Hello again, physics students. This is a little tutorial on the section 2.2 in the book on uniform motion, and leaving off with something we talked about in class, which is the first of a few kinematics equations. Hooray! This is an equation that describes how the position of an object will change with time, provided, and this is important, provided that the velocity of this object is constant. If it is constant, then this should tell you the position at any time t. This term here, which is called x final, it's often called final position, but it doesn't mean final as in last ever position. It just means the position at time t that you specify in the math model over here. V stands for the average or constant velocity. If the object is changing velocity, you could put the average velocity in here and also get values of x final for x initial. T is time, and then xi is the initial position of the object. And again, initial position doesn't mean first ever position of the object ever in the history of ever. It means at time zero. When time is zero, where is the object? It's at its initial position. So just using this equation to do problem solving, it could be a question like this, where I wrote it out here in this wonderful typeface. A ball rolls in a straight line at constant velocity. It has an initial position of 0.6 meters and a velocity of negative 0.2 meters per second. At what time will it reach a position of negative 3 meters? And one of the ways to approach this problem, and I suppose you could graph it, but using the math model is nice and simple. You could approach it in the following way. Say, take our math model, which is appropriate because it said in the problem this object has a constant velocity. And I could just circle all the things that were given. I mean, if I just peruse the problem here, I'm told explicitly initial position. It's something that I've been given. I'm told the velocity of the object. That's also something I've been given. And I'm looking at to reach a position of negative 3. So that's given as well. And it's clear now that I need to solve for time, which they tell us anyway, but it's kind of obvious from the only thing not in the equation. And plugging in those numbers, I'll have negative 3.0 for my position. The velocity is negative 0.2. T is what I'm solving for. And I have an initial position of 0.6 meters. So 0.6. I'm putting in the parentheses to make it look a little bit more clean for you. And then use algebra to solve for t. And if you solve for t, you could subtract 0.6 from both sides and then divide the negative 0.2 on both sides. And if I do that quickly, and you can try it too if you'd like. I get 18 seconds. T is equal to 18. I'll go 18.0 seconds. And that's kind of an S. So it'll take 18 seconds for the object to get to this position. If I made a graph, it would go off 18 seconds before I got to this position, so on and so forth. And we'll get some practice in using that. Going on to the next slide. We introduced something that we've been talking about in class already, unless you haven't been in class and you're viewing this for the first time, but it's the idea that not only can we make position versus time graphs to describe the motion of an object, we could also use velocity versus time graphs. And I wanted to show you a quick example of that as well. Here's a motion depicted by a position versus time graph, also depicted with this representation. Again, we're really focusing on multiple representations, like multiple ways to describe the same thing. So this shows an object moving to the right pretty fast, but not for much time. And then it suddenly moves to the left, kind of slowly, for a significantly larger amount of time. And you see that here too, that for about 3 seconds, the object is traveling in the positive direction. And I see that because the slope of our position versus time graph tells us the average velocity. So for the first 3 seconds, the average velocity and also the instantaneous velocity, the velocity at any instant, because this velocity is constant, the slope of this graph is constant. We're in the positive direction, and it's steeper. This section is steeper than this section, which is less steep. It has a negative slope, so the object's moving to the left and slower, and for more time. You can see that 3 seconds is where this change occurs. And so from 3 seconds to 10 seconds, it's traveling slow and to the left. From 0 seconds to 3 seconds, fast and to the right. And if I find the slope of these segments, like if I find the slope of this segment here, if I do rise over run for this, it looks like we're going up 6. So the average velocity for the first segment, which will also be the instantaneous velocity for the first segment, is final position minus initial position divided by final time minus initial time, which is 6/3, which is 2 meters per second. If I do the same thing for the second segment, the final position is 5. The initial position is 9, or the final position from the first segment. See, 5 minus 9, we're going to end up getting a negative number in the numerator, so a negative average velocity. And in the time duration, we're going from 3 seconds to 10 seconds, so that's 10 minus 3, final minus initial. And if I work out that math, 5 minus 9 is -4. 10 minus 3 is 7. So -4 divided by 7 gives us -0.57. So I can represent this motion with a velocity versus time graph, where the first segment has a constant velocity of 2 meters per second. And I can show that by going to my velocity graph. From 0 to time 3, I need to represent a constant velocity of +2. And here's where that number is. This is the +2 velocity. And if it's going to stay constant, that means that this graph can't go up or down. It's going to be at 2 meters per second for all 3 of those seconds. And then suddenly, the velocity changes. It changes to -0.57 meters per second for the rest of the duration. And I can represent that down here. Here's -0.5, so -0.57 is going to be somewhere down here maybe, and it's going to be really low on the screen, but I'll try to represent it by drawing, again, horizontally across, because the velocity is not changing with time. And turns out it's actually kind of complicated to draw a horizontal straight line with this pad, but if I go slow enough, I think you get the idea. To show that we're going from this spot to this spot instantaneously, oftentimes we draw a dashed line downward. The dashed line means it's not really a mathematical function. We're not actually going from this velocity to this velocity and having all the velocities in between. It's an approximation. It talks about it in the book as well. But this picture gives you a sense for an object traveling at a constant fast velocity in the positive direction, and then suddenly a negative velocity. One other thing that we've never seen before. Graphs, as we've seen, have other meanings to them aside from just what's on the x and the y-axis. You can look at a graph's slope and get information. Now, the slopes of these graphs are 0. But I would like to talk about a phenomenon that we may have never seen before, which is the concept of looking at the area under a graph. And by area, I mean the space between the function and the time axis, in this case, or whatever the x-axis is. So this rectangular space here is the area under the graph. And then for this one over here, again, it's the space between the function and the axis, so it's above the function over here. So the area I could find by just doing length times width. If I look at this rectangle, its length here is 3 seconds, and its height, or width, is 2 meters per second. So I have 2 meters per second times 3 seconds, and that gives me 6 meters. And the area is telling me the displacement. If you look for the first 3 seconds from here to here, this displacement is 6 meters. And you can see that in the graph here, going from 3 to 9 meters is a displacement of 6 meters. If I look at the area underneath here, if I do length times width for this, the velocity is actually negative. It's negative 0.57 meters per second. So areas under the graph get a negative number times the length of this rectangle from 3 to 10. This length is 7 seconds. So if I do negative 0.57 times 7, I end up with negative 3.99, which is really negative 4 meters. And if I take a look here again, from this time here, from 3 seconds out to 10 seconds, my displacement is to the left. It's negative. And it's 1, 2, 3, 4 meters. So I get a displacement of negative 4 meters for the second part of this motion. And again, I can see that on the graph. If I go over here, we finish at a position of 5. So from 9 meters to 5 meters is negative 4 meter displacement. So I can find the total displacement of this object for all 10 seconds by adding these two together. The total displacement from 0 to 10 seconds will be 6 plus negative 4, which is 2 meters. And the object does end up 2 meters to the right of where it started. If it started here at time 0 and it ends here at time 10, we're 2 meters to the right. It's positive. But you can also see distance. If you just take a look at the magnitude of the areas and get rid of the negative sign for this part, if you just add these two areas without positive or negative signs, you get the total distance traveled. The total distance is 6 meters to the right plus those 4 meters to the left, or 10 meters of total distance traveled. If you follow this trajectory all the way around, you'll get 10 meters.